Right, so I'm going to introduce some basic concepts about Wi-Fi cryptography, and hopefully we'll be able to see some of the history that's happened within Wi-Fi, and possibly even some of the problems that we've actually faced. So there's what our infrastructure looks like. So there's basically two types. One is what we would call pre-shared key. That's a home network. And with that, we typically have the authenticator inside the access point, and then we connect to it with what's called here a supplicant. And you must provide the right credentials to be able to access the local Wi-Fi network. On most corporate infrastructures, the users are normally allowed to migrate, and it also integrates with the Windows domain infrastructure through some sort of LDAP infrastructure. So there is some synchronization between the centralized authentication server and the Wi-Fi infrastructure. So when Bob, in this case, wants to authenticate himself onto the network, his request is then sent through to typically a Radius server to be able to gather the authentication. We might also have a PKI server for certificates if we ask our supplicants to be able to sign things. Then we need a key pair for that. So the encryption we'll see coming along is RC4, 40-bit or 128-bit. Oh, now we have a block cipher of AES. For some of the authentication methods, we can use 1x EAP, and we can use a whole lot of things, even biometrics, to be able to authenticate ourselves onto the network. Okay, so there's the basic infrastructure that we actually have. Okay, so really we need to understand where we've been, and especially the disaster that was caused by the web Wi-Fi infrastructure. A complete and absolute disaster which virtually broke many of the rules inside our crypto systems. Okay, so there's what we have. As we said before, we can have an authentication infrastructure like this. Okay, so WEP, as it was really designed for systems that had fairly low processing capabilities. So when it was introduced with a very small 40-bit key. Okay, anybody that knows anything about crypto will know that 40 bits isn't really enough, and that we should probably be looking at about 72 bits at least to have any sort of security. So I brute force 2 to the 40 isn't a large number, a large enough number that would stop us from actually breaking it, trying out all the keys in an instance, and then all the keys on something like a GPU, and to be able to crack the key. So we're using a stream cipher. So what happens is that we bring in what's called an initialization vector, or a little bit of salt, to make sure that we don't have this problem around brute force. Okay, so the 24-bit IV or salt was added into the method, the RC4 method. We took our key, and then that key was added in, and we create what's called a pseudo-infinite key. That we then take the plain text stream, and we take each bit one at a time with our infinite key, and we exclusive OR, and we produce the output. So a 1 and a 0 in exclusive OR gives us a 1, a 1 and a 1 gives us a 0, and so on. And the great thing on the other side is that all we have to do is reverse this operation. The other side should have the IV and the secret key. Hopefully, if we've shared it correctly, they then produce the same key stream, the exclusive OR it back again, and then out pops the plain text. Nice and simple. Doesn't have the complexity that would be required for a block cipher of storing memory and then chaining things on and so on. Nice and simple. RC4 is a great encryption algorithm for that. Okay, so that was the setup, and that works fine until it was discovered that within a reasonable time period the IV will repeat again, and then what we can do is we can exclusive OR the output with the new with the same IV that has come around, and through statistical analysis we can actually crack the cipher. Okay, so that was the setup that we had there. Okay, so we have our RC4 method goes in. We then create the output, which is XORed with the data stream. On the other side, we just do the same again. We create that same key, and everything's fine. So we must send the IV value with the data, because it wouldn't be possible for the other side within a reasonable time limit to be able to determine what the IV vector is and generate the same data stream. Okay. So RC4 works like this. So we create what's called an S-box. So an S-box is a way for us to scramble the data, but for it to be able to be reversible. So it's reversible in this case because we just exclusive OR it back. So the first part here is our S-box creation. We take our key, we determine the length, and then we do some scrambling of it here. So we swap and we move things around and just generally create a new S-box based on the key. And then the other part, what we do is that we create an infinitely long key, an infinitely long pseudo stream from this S-box. And because it's going to be really difficult for us to return back infinity bits, in Python we use a technique called yield, and yield allows us to be able to return the values. Look, you see here we have an infinite loop, which isn't very good. If that keeps running, then it's going to keep running forever and ever, crunch the system. But with the yield, what we can do is we can actually leave the method here, and then we use the next method for whatever is returned here to be able to get the next byte. Okay, so what this is going to do is that each time we say next, 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 it will return the next byte of the key stream. I hope that makes sense then. Okay, so we'll have a look at a quick example of what that actually looks like. Okay, so I've got some text here of hello. I've got a key stream of this. Okay, with the RC4 we can have any size of key from 0 bits, don't think that would be very good, to a key size of 2048 bits. So I'm using just a sample test vector here. So when we run this, we'll just change this. We can see here that our key stream, so I've only shown 16 bytes of the key stream here, but obviously it would go on and on and on and on and on, as big as our data that we have. But every single time if I change the hex value, then I get a new key stream value. We take hello, and then we'll take our key stream, we exclusive OR them together, and that's the cipher stream. So what I've shown here is what the S-box will look like with the keys that we have here. So there's the S-box. You'll notice that no value repeats there, because all we're doing is shuffling the key stream. So if we try another one, we should see a different key stream and a different S-box for that one. I'll try again, and then we get another new S-box. Okay, so as the S-box is scrambled, it's like taking the values from 0 to 255 and then shuffling them around. That gives us our S-box. We then go into the pseudo-random method, and then that will scramble the key stream based on that. As I said, the yield is there for us to be able to get the key stream whenever we want it. So just to check, okay, so for 40 bits, this is a little test here, test stream. So I'm going to put the hex value in here. Okay, so the key stream it should produce is this one here for 40 bits. So it should start with B2 and end with A8 for the first 16 bytes. And fingers crossed, B2 and 1/8, that's fine. 1/8 here, so this one here. I've obviously printed that 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oops, I haven't printed enough there, but that would end there. So we can also check RC4 with a longer stream. So this is 128 bits. And this time we should get 9A at the start of the key stream. And we do. Okay, so there's the S box that we've got here. So as I said, it's scrambled, no two values should repeat. If they do, then it's going to cause lots of problems in unscrambling the data for S boxes. Okay, so that's the that's RC4. The other problem that we had with Inside Web was that we did a very simple checksum by taking all the bits in the bit streams and aligning them with 4 bytes at a time, aligning them one at a time, and then taking an XOR of each column. And what happens there is that the intruder can then flip bits and make sure that the checksum stays the same. So in this case, Eve goes and captures the data and then flips a few bits. And in this case, she's flipping the bits in the IP header, which means that rather than going to alice.com, she goes to mal.com. But you can see the bits here are still the same. They still check out the same checksum. But the biggest weakness was that eventually the IV value came around again. So we've got 60 million 2 to the power 24 different IV values, and it's going to come round after a few hours that the same IV value comes out again. So what happens is that Eve basically captures all the ciphertext and waits for the same IV value to come around, and then she XORs the two ciphertexts together, and then through statistical analysis you can actually reverse the data. Okay, so here's an example here. So if I use hello, yeah, and then I have a message of hello here with a key, so I'll just make the key bell. Okay, so there's a ciphertext here, and we get that, and we get that because it's the same IV. And then when we run it, let's make that hello. When we exclusive OR them together, we see we have 0. So with that, we can actually, through statistical analysis, we should be able to identify our cipher stream. Okay, so you can see here that only the last byte has actually changed there, and we can actually tell it's a change. So E is the most common letter, so often we would use that type of analysis to be able to get the stream, the data stream. Okay, so some of the problems is a very small IV value, 24 bits. The keys themselves were constructed in a very weak way. There was a lack of protection against replay. It was possible for Eve to be able to take a cipher stream and then play it back. There was no way of actually defining a sequence of data frames. There was a lack of message tampering with it in there, and it also used a direct master key, and there was no way to update the keys within the system. So meet WPA2 and WPA, which solved most of the problems, but still not perfect. Okay, so the ways that we can apply security is obviously to use IPsec. If you really want security, then basically you've got to tunnel. We're using a proper tunneling protocol, not SSL, but to use IPsec. Within wireless standards, we've got encryption using RC4 as we've seen, or now AES. Authentication, we can use a whole lot of authentication methods if we need. Okay, so the 1X framework actually defines ways that we can authenticate, we can negotiate keys, and so on. So some of the methods that we use within our authentication infrastructure, Leap is a way that we can actually provide a username and password, and the other ones will typically involve some sort of MAC address or digital certificate in there. The great advantage of 1X is that it fits on most network infrastructures. So the two main standards that were promoted were WPA, and then that used an extension of the WEP, and that we increased the IV value to 48 bits and also put in a better integrity checker, along with having a session key rather than a global key. WPA2 adds a block cipher of AES. Okay, so the way that WPA works is there's what's called a four-way handshake. So the password itself that's created inside a pre-shared key is never passed over the network, but they both agree on a secret and then share that. So we create what's called the pairwise master key, or PMK, and this is the way that we set up. The access point itself sends a nonce or a random value to the station, and then from there we send back its nonce value and some sort of message integrity check value. After that, we send back what's called the global temporal keys. That's used for multicast and for broadcast communications, and then there's an ACK at the end. The hash that we produce is a hash based on the pre-shared key that we're going to use, the SSID, and we generate that for a number of rounds and for a certain size of hash. Okay, so let's have a look at the hash value that we actually produce, and it's this hash value that can be cracked possibly. So it uses PBKDF2 because it's a fairly slow method of hashing, which slows down the cracking. Okay, so here's some Python code here that allows us to build that up into our key, or the hash of our key. Okay, so we'll try that message with that key. Here is the pairwise master key that we get for that SSID and that passphrase, but also for these parameters here that we've used. Okay, so there are 4096 iterations of PBKDF2 from there, and we produce a 256-bit hash for us, and that gives us an HMAC SHA-1 type format hash. Okay, so that's that. So if you're interested in how that can be cracked, then there should be a little demonstration here. Okay, thank you.